Hi, my name is Hope Lee, and this is my video lab report for lab number 1. In this lab, we focus on examining the constant motion of an object and comparing it to a computational model we built. The purpose of the lab was to use the initial conditions derived from tracker data to record and analyze the constant motion of an object moving at a constant velocity. As a brief preview of my results, I can say that the computational model had a significant difference in results over time when compared to my observed model. There were a few fundamental principles needed to tackle the lab. In fact, the whole lab is based around Newton's first law, since our object is supposed to remain in motion at a constant velocity unless acted on by external force. The main place that this could be identified in the lab is when I initially rolled my chosen object, which was an expo marker, down the table. Newton's second law, with net force equaling mass times acceleration, helped configure the net force for the coding and identify the initial position, velocity, and object's mass. Here's a clip of my tracker data. I input the video of my expo marker rolling down the table, and I calibrated the screen to be 1 meter because when I initially rolled my object, it was in front of a meter stick to know its distance once rolled. I set up my coordinate axis, the purple in the video, at the initial position of the object so that it could be used with the origin as a position of 0, 0, 0. Now on to the calculations. Here are some calculations used in the lab. I looked up the mass of an expo marker and converted it to kilograms. I found the initial position by subtracting the second position from the first position, and the same with the time intervals, and divided them by each other to get the velocity. The information was input into the provided starter code on GlowScript, as can be seen in the slide. Further, in the loop code section, the velocity update formula and the position update formula were used to predict the velocity and position as a function of time over time. They were included in the GlowScript code as seen in the slide, and using Newton's second law, the net force was proven to be 0 since the mass was a scalar and the acceleration for a constant motion is always 0. Now onto the coding. The entire code seen on the screen is from the velocity update formula and position update formula, where we're trying to loop the code to get the position and velocity over time. I multiplied delta t by 100 to make sure that the computational model didn't stop before the video ended, and they are seen on the slide. Onto the computational model. The computational model is seen moving at a constant velocity and position. The yellow dot is the object at its initial position, and it moves constantly. Both graphs show that the object had the same constant velocity and position as seen on the position versus time graph, as well as the velocity versus time graph. Now on to the results. The observed position is the blue line, while the computational model is graphed in orange. As seen on the graph, they both seem to be moving along the same until the 0.05 mark, where they split off, showing that the observed model did not follow the same physics as the coding predicted. If the axes were to be flipped, this is what would happen. I chose the coordinate axis so that the position would be positive as soon as the object started its motion, making the right positive and the left negative. If the axes were flipped, there would only be a change in the position sign. The graph would be in a downward position instead of upward, but it still indicates that an additional force decreased the velocity and final position over time. It's not realistically possible to see how many forces are acting on the object to lead to net force equaling 0. There are always infinite and hidden interactions on the object, so figuring out which ones are there is really hard. Some possible forces that could be causing these results are friction from the table, the initial force from the hand pushing the expo marker, and gravity. I can confirm, based on the observed model, that forces were acting on the model, but I can't confirm how many because they weren't canceled out to make the net force 0. In all, Newton's first law was proven, and Newton's second law helped verify the first law. Thank you.